Hello everyone, welcome to the auto-scaling hardware-agnostic machine learning inference with NVIDIA Triton and ArmNN session. This is Wei from NVIDIA. Co-presenting with me today is Josh Miner from ARM. Here's what we are going to cover today. First, we will introduce what model serving is to help you understand how NVIDIA Triton Inference Server manages and deploys machine learning models in production. Then we will take a look at the ArmNN inference engine. As a matter of fact, ArmNN already enables accelerated machine learning inference on billions of ARM mobile and embedded devices. To help you get the best of both worlds, ArmNN and NVIDIA Triton are now integrated. The product has been released to select early access partners. To wrap up, we will walk you through customer success stories. Model deployment is not an easy task. Across the spectrum, the developers face different challenges, including diverse software frameworks and inference requirements, hardware complexity and underutilization, scalable machine learning model serving, and orchestration. For data scientists or application developers, your primary challenge is the diverse software frameworks and inference requirements. Data science today are using a variety of frameworks like TensorFlow, PyTorch for your production models. However, as serving applications typically only support one of these frameworks, the developers have to convert the models between different formats or use various serving applications for different models. In the meantime, applications have independent inference requirements. Some of them require real-time processing. For example, Uber Eats. When a user orders food through the service, it needs to calculate the estimated time to delivery in real time. Other inferences may require batch processing to maximize throughput. As an example, if you're developing a service like a Netflix recommendation system, it doesn't make sense to generate a list of recommended movies for the user each time when they log on. Instead, you can generate these recommendations in a batch fashion. For embedded developers, your challenge is the increasing hardware complexity and hardware resource utilization. Let's start with hardware complexity. We can now run machine learning inferences on the cloud or data center, the workstations, or embedded edges. Inference hardware architecture can be CPU, GPU, NPU. We need one single serving application that gets the best inference mileage out of the disparate hardware architectures. The second aspect of the challenge here is the hardware utilization. In deep learning applications, inference drives as much as 90% of the compute costs of the application. Accelerated computing power is often oversized. The third challenge is DevOps. How to scale machine learning model serving and orchestration. For example, detecting specific events in a live sports broadcast results in a large payload ranging from hundreds of megabytes to gigabytes. You need to run the algorithms on CPU, GPU clusters. Versus using a machine learning model for human detection only requires hundreds of kilobytes. An embedded CPU is powerful enough to process the workload. You need serving applications that can adjust to a variety of payloads dynamically. Inference serving comes into the picture to address the model deployment challenges we just touched on. Inference serving is the final step to a successful machine learning project and arguably the most challenging part of MLOps. This is because your infrastructure and deployment strategy is tied to user expectations, business rules, and technologies you're already using at your organization. There are different machine learning inference serving tools on the market. The popular ones include Google TensorFlow Serving, Facebook Torch Serve, KF Serving. Usually, these tools only support one machine learning framework or specific hardware infrastructure. NVIDIA started the Triton open source project a few years ago to address the challenges companies face in machine learning model production. Triton adopts a client-server architecture. The Triton client sends inference requests to the server, which pulls the models from the model repo for inference, and sends the inference results back to the client. The programming interface between client and the server can be HTTP or gRPC. Triton Inference Server supports both CPUs and GPUs. To scale out, you can also integrate it with Kubernetes for multiple cores, multiple GPU support. To increase hardware utilization, Triton supports dynamic batching and concurrent model execution, which means you can run multiple copies of a model and multiple machine learning models in parallel. Triton also uses the extensible backend for multiple frameworks, hardware architecture support, and forward compatibility. TensorFlow, PyTorch, or Linux can all be configured as backends. NVIDIA Inference Framework TensorRT is a backend for NVIDIA GPU acceleration. Triton also supports custom backend interfaces for third-party extensions. Triton is the backbone of the machine learning service, including Microsoft Azure, Google Cloud Service, American Express. As you can tell, Triton is beneficial to developers for large-scale production deployment. To bring the same benefits to ARM-embedded developers, Triton for embedded platforms was launched. Both the Triton Inference Server and the client can run out of an embedded edge device. ARM also extended the Triton backend with ArmNN. The acceleration unlocked by ArmNN opened the doors to a surge of new machine learning applications. As a result of this, the features we discussed in the previous slides are inherently supported. What does this mean to developers? Because of Triton's hardware-agnostic architecture, you can run the same Triton stack on NXP-MX, Raspberry Pi, or NVIDIA Jetson family of devices and use different Triton backend to accelerate machine learning inferences regardless of the underlying hardware. Triton's concurrent model support mechanism and the dynamic batching feature enable applications like autonomous systems, robots, where you may need multiple machine learning models to coordinate on specific tasks. Hardware utilization and machine learning performance metrics are provided as part of Triton. For developers, you can use C and Python APIs to program. Now I'm handing over the presentation to my colleague Josh to dive deep into this exciting product.
Thanks, Wei. Hey everyone, my name is Josh Miner. I'm a research engineer here at ARM. And in this first portion of my presentation, I'm going to go ahead and introduce ArmNN. ArmNN is a software library developed in-house here at ARM that intends to bridge the gap between existing neural network frameworks and underlying IP. It enables users to translate their existing models, which are saved in a variety of formats, including TensorFlow-Lite, PyTorch, or Onyx, into a representation that ArmNN understands and can execute optimally on underlying ARM hardware. It abstracts away the underlying hardware that the model is going to be ultimately executing on, which is fantastic for developers. Further, these same developers can maintain their existing workflows and tooling for training and producing inference-ready models, and at the very end of their pipeline, they just pass the inference-ready model to ArmNN for optimized execution on the underlying hardware. The library is optimized for Cortex-A CPU, Mali GPU, and Ethos-N NPU. It gives you the ability to leverage graph level and kernel level optimizations for these networks. It's ready for multi-core out of the box, including the Ethos-N NPU, and it's an open source project licensed under MIT. ArmNN provides substantial performance uplift in inference execution time as compared to many other industry solutions. So in the graph on the left, we're comparing the performance of ArmNN against 6 other popular software libraries. And the graph is showing how much faster ArmNN can execute a neural network on ARM-based hardware in comparison to these other solutions. So for instance, for Inception v3 on Mali GPU, we're looking at a performance uplift of 1.7x, and similar numbers for a big Cortex-A ARM CPU or a little Cortex-A ARM CPU. This market-leading performance is enabled by our intimate knowledge of the underlying architectures, which allow us to implement target-specific optimizations. In addition to this, the ArmNN solution is continually evolved using advanced network optimization techniques, including fusion and device-specific tuning. And finally, optimizations for ArmNN are focused on the most common operators across the most popular network architectures. So there are a couple different ways that you can integrate ArmNN with these existing ML frameworks. You can take a TensorRT model and you can do a layer-by-layer translation to the ArmNN format where it will ultimately be executed by the ArmNN runtime. You can do the same thing for a PyTorch model, which is translated to an Onyx model, which is then translated to the ArmNN format. In a slightly different fashion, you can take models which are targeting the Android NN API and then leverage the ArmNN driver, which implements that API to accelerate your model inference. And finally, for the focuses of this presentation, we're looking at the ArmNN TFLite delegate specifically. So the ArmNN TFLite delegate is a software module which plugs directly into the TFLite runtime. It provides greater flexibility for Android developers over the existing neural network API, and that's because you still get all the same ARM-specific CPU and GPU optimizations that ArmNN provides, but the difference is that for any ML operation which is not supported by ArmNN, it falls back to the default TFLite CPU runtime. So this is great because now we can support all TFLite models, and there's no issues where if you have an obscure operator which is not supported by ArmNN, not being able to leverage ArmNN acceleration for that model. And of course, this is also suitable for non-Android environments like Linux, which is what we're using for our target platforms for Triton. So how do Triton and ArmNN fit together? The motivation for this backend is with the existing Triton releases, they're primarily focused on x86 machines with support for NVIDIA GPUs, as well as the NVIDIA Jetson family, which is a set of embedded platforms, which are ARM v8 architecture with CUDA GPUs integrated into the system. By leveraging TFLite, we can run optimized models for many problem domains on these embedded edge devices like the NVIDIA Jetson family, for instance, or things like Raspberry Pis. Existing Triton inference optimizations do not have support for ARM IP like ARM Neon technology or Mali GPU technology. And so by creating this backend, we're enabling those acceleration technologies to be used for ML inference. And finally, as an example, on NVIDIA Jetson devices, we have a CUDA GPU where you can run a model in an optimized fashion, but you still have this 6-core CPU unit, like in the case of the Jetson Xavier NX, which is largely sitting idle in some cases. It's just passing work to the CUDA GPU. So why not leverage ArmNN here to improve your hardware utilization to where I can run another model on that set of CPU cores in an optimal fashion and really maximize my hardware utilization. The following is showing how you can leverage ArmNN acceleration with Triton in 4 simple steps. So the first thing you need to do is generate a TFLite model using the TensorFlow tooling. So TensorFlow provides a TFLite conversion tool where you can take a saved TensorFlow model and translate it to the understood TensorFlow Lite format. Now with that saved TensorFlow-Lite model, you move it into the Triton-defined model repository. So the model repository is just a special directory structure which Triton expects, where it can find information about the model itself and how it should be served, as well as the model file itself. Now, with the model file moved into the Triton directory structure, you have to then generate a configuration file for this supplied model. And I'll go into an example of what that looks like here next. And then finally, you need to run Triton on the target device and then use the Triton-defined client libraries to request inference from the Triton Inference Server, which has your TensorFlow-Lite model loaded. Here's an example of what a Triton model configuration file looks like when leveraging the ArmNN TFLite backend for MobileNet v1. So the first thing to note here is that we specify that we are using the ArmNN TFLite backend for this particular TFLite model. Next, we can specify a maximum batch size. Right now it's set to 1, indicating that for each forward pass of the model, we're going to be using a batch dimension in the tensor of 1. But for models that support a variable batch dimension, you can actually increase this value to 3, 4, 5, or some arbitrary value as long as the underlying TensorFlow-Lite model would support that. So if it were 4, you can support a client sending over 4 images at once and getting a single response back for those 4 images. We next specify metadata around the model and its inputs. So the input for this model has the name input within the model itself. It's a floating point 32 model. It has tensor dimensions 224 by 224 by 3. And in this case, because we're dealing with an image tensor, Triton allows you the ability to specify the data layout of that image tensor. Next, we also do the same thing, but for the outputs of the model. So in the same fashion, we give the name of the output, the data type, the dimensions of the tensor, and then in this case, because we're using an image classification network, we can optionally specify the labels file that was used during the training of this image classification network. And in this case, when a client requests inference, it'll get back the rich classification name as opposed to just the tensor index. Now finally, the most important thing to consider here is that for this particular model configuration, we want to tell Triton that we want to leverage the ArmNN acceleration on both CPU and GPU. So by specifying this optimization parameter, we're telling Triton to bring up an instance of the ArmNN TFLite delegate before it starts executing the model. So now we'll look over some initial performance figures for this ArmNN TFLite backend. The first set of hardware we tested on was a Raspberry Pi 4 with 4 gigabytes of RAM, and the Raspberry Pi 4 has a quad-core Cortex A72 CPU. We are using a single local inference client, so it's sending information over localhost. We have a single CPU instance for each of these models loaded in memory. We're using Triton's gRPC transport, and we are running with a TensorFlow-Lite v2.4.1 version of the backend. And we can see we are comparing the TensorFlow-Lite default runtime with Rui acceleration enabled. We are also looking at the TensorFlow-Lite runtime with the NN Delegate enabled, which provides accelerated floating point ML operations on CPU. And then finally, we're looking at the TFLite runtime with ArmNN CPU acceleration. And we can see that for each of the models that are specified here, we are seeing significant performance uplift as compared to the other TensorFlow-Lite runtimes which are available. Most significantly, we can see with VGG16 that we are seeing a performance uplift of 4.5x in terms of the throughput the client perceived, and a latency reduction of 4x for that same client. So the numbers are very, very promising here. It's now running the same benchmark, but on a Rock Pi 4, which has a big. LITTLE configuration for its CPU. We see substantial performance uplift again for the TFLite with ArmNN Delegate enabled. Again, with VGG16, we're seeing a very substantial performance uplift in terms of throughput improvement and reduction in latency of 3.5x and 2.74x respectively. We can see that it is slightly outdone by the TensorRT with XNN pack for SqueezeNet v1.1, but you can see in comparison to the default TensorRT runtime, you still have the uplift with ArmNN on CPU. For the next steps in this work, we're looking at ways of leveraging ArmNN for some of the other existing NVIDIA Triton backends. This is with the intention of providing a full-fledged solution for accelerating inference in the ARM data center space. And with that, I will go ahead and pass it back to Wei, who will go over some customer success stories so far.
Thank you, Josh. For data scientists and application developers, the Triton and ArmNN integration unleashed Triton and ArmNN's scalability and acceleration. With Triton's unified interface to multiple software frameworks and hardware architectures, application developers only need to write application once and run it across different AI frameworks and hardware. For SoC and embedded developers, Triton's multiple backend support and hardware-agnostic approach ensure the best inference performance across hardware, which means without digging through the hardware stack, you can benefit from a higher hardware utilization rate. For the DevOps teams, your solution can easily scale up and scale out to cloud and data centers. Let's switch gears to talk about customer success stories. ArmAI ecosystem partner and NVIDIA's Inception program member Nota, a Korean startup specializing in edge AI. Their Nespresso is the industry's first hardware-aware AutoML and software optimization platform. Users can define their latency, accuracy, and hardware requirements, and Nespresso generates the most resource-efficient model based on users' criteria. The tool is fully compatible with Raspberry Pi and NVIDIA Jetson family of devices. If you want to check it out, please register using the link at the bottom of the slide. After test driving Triton and ArmNN backend, Nota was impressed by the solution's robustness, super performance with Triton's multiple requests, multiple model support, and the 26 to 38% latency improvement enabled by ArmNN. With Nespresso, Triton, and the ArmNN backend, Nota developed and operated diverse commercial-level AI models, including intelligent transportation system, sign recognition, human detection, and many others. Here's the story of Darwin AI, another ARM ecosystem partner and NVIDIA's Inception program member. Darwin developed machine learning models for steel strips surface inspection. This type of steel strips is commonly used in vehicle frameworks in automobile and aircrafts. Common defects include scratches, inclusions. On a manufacturing floor, using embedded devices for edge AI inspection is gaining popularity. However, hardware resources sometimes underutilized. In our case here, with Triton's multiple model concurrency support and ArmNN's acceleration, Darwin was able to maximize the hardware throughput by running multiple copies of the same model in parallel and still meeting their latency requirement. Also, disparate hardware architectures used in factories result in deployment challenges. Triton can hide the complexity of different CPUs, GPUs. As a result, Darwin deployed one single serving application across different hardware architectures, leveraging different backends for efficiency and scalability. Here are some resources to get you started with the Triton ArmNN backend. Please check them out. NVIDIA's anchor event GTC Fall will take place between November 8th to 11th this year. It's a free virtual event that opens to everyone. Josh and the two Triton ArmNN backend early access partners will introduce the product at the conference. Please register with the URL here. We look forward to meeting you again. Thank you very much for joining today's session.